consistency. Transaction lock time limitations. Lock time has the limitation that while it makes it possible to spend some outputs in the future, it does not make it possible to spend them until that time. Let's explain that with the following example. Alice signs a transaction spending one of her outputs to Bob's address and sets the transaction lock time to 3 months in the future. Alice sends that transaction to Bob to hold. With this transaction, Alice and Bob know that Bob cannot transmit the transaction to redeem the funds until 3 months have elapsed. Bob may transmit the transaction after 3 months. However, Alice can create another transaction, double spending the same inputs without a lock time. Thus, Alice can spend the same UTXO before the 3 months have elapsed. Bob has no guarantee that Alice won't do that. It's important to understand the limitations of transaction lock time. The only guarantee is that Bob will not be able to redeem it before 3 months have elapsed. There is no guarantee that Bob will get the funds. To achieve such a guarantee, a time lock restriction must be placed on the UTXO itself and be part of the locking script rather than on the transaction. This is achieved by the next form of time lock called check lock time verify. Check lock time verify CLTV. In December 2015, a new form of time lock was introduced to Bitcoin as a soft fork upgrade based on specifications in BIP65. A new script operator called check lock time verify CLTV was added to the scripting language. CLTV is a per output time lock rather than a per transaction time lock, as in the case with time lock. This allows for much greater flexibility in the way time locks are applied. In simple terms, by adding the CLTV opcode in the redeem script for an output, it restricts the output so that it can only be spent after the unspecified time has elapsed. CLTV doesn't replace lock time, but rather restricts specific UTXO such that they can only be spent in a future transaction with lock time set to a greater or equal value. The CLTV opcode takes one parameter as input expressed as a number in the same format as lock time, either a block height or Unix epoch time. As indicated by the verify suffix, CLTV is the type of opcode that halts execution of the script if the outcome is false, if it results in true execution continues. In order to lock an output with CLTV, you insert it into the redeem script of the output in the transaction that creates the output. For example, if Alice is paying Bob's address, the output would normally contain a P2PKH script like this: DUP hash 160 Bob's public key hash equal verify check. To lock it to a time, say 3 months from now, the transaction would be a P2SH transaction with a redeem script like this: now 3 months, check lock time verify, drop DUP hash 160 Bob's public key hash equal verify check sig, where now plus 3 months is a block height or time value estimated 3 months from the time the transaction is mined. Current block time plus 12 960 blocks, or current Unix epoch time plus 760,000 seconds. From now, don't worry about the drop opcode that follows. Check lock time verify. It'll be explained shortly. When Bob tries to spend this UTXO, he constructs a transaction that references the UTXO as an output. He uses his signature and public key in the unlocking script of the input and sets the transaction nlock time to be equal or greater to the time lock in the check lock time verify Alice set. Bob then broadcasts the transaction on the Bitcoin network. Bob's transaction is elevated as follows. If the check lock time verify parameter Alice set is less than or equal to the spending transaction's nlock time, script execution continues, acts as if no operation or no OP code was executed. Otherwise, script execution halts and the transaction is deemed invalid. More precisely, check lock time verify fails and halts the execution, making the transaction invalid. If source BIP 65 1, the stack is empty, or 2, the top item on the stack is less than 0, or 3, the lock time type height versus timestamp of the top stack item and the nlock time field are not the same, or the top stack item is greater than the transaction's nlock time field, or the sequence field of the input is 0x FFF. After the execution, if CLTV is satisfied, the time parameter that preceded it remains at the top item on the stack and may need to be dropped. With drop for correct execution of subsequent script opcodes, you will often see check lock time verify followed by drop in scripts for this reason. By using nlock time in conjunction with CLTV, the scenario described in transaction lock time limitations on pages 157 changes. Because Alice locked the UTXO itself, it is now impossible for either Bob or Alice to spend it before the 3-month lock time has expired. By introducing time lock functionality directly into the scripting language, CLTV allows us to develop some very interesting complex scripts. The standard is defined in BIP 65 check lock time verify. Relative time locks. Nlock time and CLTV are both absolute time locks in that they specify an absolute point in time. The next two time lock features we will examine are relative time locks in that they specify as a condition of spending an output an elapsed time from the confirmation of the output in the blockchain. Relative time locks are useful because they allow a chain of 2 or more interdependent transactions to be held off chain while imposing a time constraint on one transaction that is dependent on the elapsed time from the confirmation of a previous transaction. In other words, the clock doesn't start counting until the UTXO is recorded on the blockchain. This functionality is especially useful in bidirectional state channels and lightning networks, as we will see in payments channels and state channels on page 284. Relative time locks, like absolute time locks, are implemented with both a transaction level feature and a script level OP code. The transaction level relative time lock is implemented as a consensus rule on the value of nSequence, a transaction field that is set in every transaction input. Script level relative time locks are implemented with the check sequence verify CSV opcode. Relative time locks are implemented according to the specifications in BIP 68. Relative time lock using consensus enforced sequence numbers in BIP 112, check sequence verify BIP 68 and BIP 112 were activated in May 2016 as a soft fork upgrade to the consensus rules. Relative time locks with nSequence. Relative time locks can be set on each input of a transaction by setting the sequence field in each input. Original meaning of nSequence. The nSequence field was originally intended but never properly implemented to allow modification of transactions in the mempool. In that use, a transaction containing inputs with nSequence value between 2320xFFFFFFF indicated a transaction that was not yet finalized. Such a transaction would be held in the mempool until it was replaced by another transaction spending the same inputs with a higher nSequence value. Once a transaction was received whose inputs had an nSequence value of 232, it will be considered finalized and mined. The original meaning of nSequence was never properly implemented, and the value of nSequence is customarily set to 232 in transactions that do not utilize time locks. For a transaction with nLocktime or check locktime verify, the nSequence value must be set to less than 232 for the time lock guards to have effect. Customarily, it is set to 232 minus 1 0xFFFFFFE. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.